Welcome to Chapter 15 on Deep Learning. Here we build a working map of modern deep learning, the family of methods behind today's most striking advances in vision and language. In 2012, a neural network won an image recognition contest by such a margin that the field changed almost overnight. Chapter 14 gave us the building blocks. Now we aim for breadth with enough depth to be genuinely useful. By the end of this chapter, you should be able to explain what sets deep learning apart from shallow networks, why it excels on complex unstructured data, what representation learning is, and how convolutional networks use convolutional and pooling layers. You should also be able to describe recurrent networks and why LSTMs and GRUs improved on them, explain transformers and attention at an intuitive level, say what embeddings are, and recognize the common challenges of training deep models. This figure shows a small convolutional network for the fashion MNIST dataset. Convolutional layers learn local feature detectors, pooling layers shrink the spatial size, and a final dense layer turns everything into class scores. Deep learning is the branch of machine learning that uses neural networks with many layers. The payoff of depth is clearest in vision. Early layers catch edges and colors, middle layers find corners and textures, and later layers recognize whole objects. Deep networks are an old idea, so why did they take off only recently? Two reasons stand out: huge labeled datasets from the internet and sensors, and a surge in computing power, especially graphics processing units suited to training networks. Better optimization, such as ADAM and smarter initialization, made deep networks trainable in practice. Open source tools like TensorFlow, Keras, and PyTorch put these methods within reach of anyone with a laptop, especially where manual feature engineering is hardest. This figure shows why depth helps. A deep network builds a hierarchy of features. Early layers detect simple patterns like edges. Middle layers combine them into textures and parts, and the deepest layers respond to whole objects. Structurally, a deep neural network is just the multi-layer perceptron of Chapter 14 grown tall, with many hidden layers feeding one another. What changes with depth is not the mechanics, but the behavior. If you remember one idea from this chapter, make it representation learning. Picture a network reading handwritten digits. Early layers see low-level pixel patterns and edges. The next find lines, loops, and curves. Then parts of digits, like the top arc of a 3, and finally complete digit shapes. The same principle carries over to text. A model can learn representations of words, phrases, sentences, and whole documents, capturing meaning rather than just spelling. For images, the workhorse is the convolutional neural network, or CNN. Unlike a plain network that treats an image as an unstructured list of pixels, a CNN stacks convolutional layers, ReLU activations, pooling layers, and fully connected layers near the end. An output layer, often softmax, then produces the prediction. The next two sections look closely at the two components that make a CNN distinctive. This figure traces a convolutional network pipeline. The image passes through alternating convolution, ReLU, and pooling stages whose feature maps shrink in size before being flattened and sent through a fully connected layer. A convolutional layer slides small filters across the input. The point of each filter is to detect one specific pattern wherever it appears in the image. Convolutional layers can produce large feature maps, and not every pixel of detail needs to move forward. The common choice is max pooling, which slides a small window across the map and keeps only the largest value in each region. Let us make convolution concrete. Take a 5 by 5 grayscale image with a single bright vertical line down the middle and a 3 by 3 filter that computes left pixel minus right pixel, so it fires where brightness drops from left to right. Convolution lays the filter over a patch of the image, multiplies the overlapping numbers, and adds them up. This equation states the operation precisely. Each output value is a sum over the filter weights times the image values they cover. It is exactly the slide, multiply, and add we just described. Because every row of this image is identical, every row of the feature map is 2, so we only need 3 positions in one row. The filter fired strongly on the right edge of the bright line and negatively on the left edge. Now apply ReLU, which clips every negative value to 0. It keeps the bright to dark edge and discards the other one. Pooling then shrinks the map while preserving the strong response, giving the small shift tolerance pooling is meant to provide. This figure summarizes the hand-computed pipeline. The vertical edge filter lights up the edge in orange while flat regions stay dark. ReLU keeps one edge polarity, and 2x2 max pooling shrinks the result. A real convolutional layer differs only in scale. It learns the filter values instead of being handed them, and it applies many filters at once to produce many feature maps. Convolutional networks underpin a huge swath of practical computer vision. Let us look at where they show up. They power image classification, object detection that locates and labels many objects, face recognition, medical image analysis that flags suspicious regions, satellite and aerial imagery, and defect detection on manufacturing lines. As a concrete example, a CNN can be trained to label a medical image as normal or abnormal. Images are spatial, but many problems are sequential. A recurrent neural network reads a sequence, one element at a time, while carrying a hidden state, a running summary of everything it has seen so far. Recurrent networks suit many sequence tasks: language modeling and text generation, speech recognition, time series forecasting, machine translation, and sequence classification, such as sentiment analysis. This figure unrolls a recurrent network over 3 time steps. At each step, the input updates the hidden state, which produces an output and is then passed forward, carrying memory from one step to the next. Simple recurrent networks have a well-known weakness, though. They struggle to remember information across long sequences. To give recurrent networks a longer memory, researchers designed gated variants, the long short-term memory network, or LSTM, and the gated recurrent unit, or GRU. The transformer, introduced in 2017, is the architecture behind modern language processing and large language models. Unlike a recurrent network, it can directly relate any position in a sequence to any other, no matter how far apart. Transformers now drive machine translation, text classification and summarization, question answering, code generation, and the large language models we will meet in Chapter 18. The engine inside a transformer is attention, and its intuition is worth dwelling on because it explains so much of modern artificial intelligence. Neural networks consume numbers, but much of the world arrives as discrete symbols, words, product IDs, user accounts, categories. The classic way to handle them is the word embedding. Embeddings appear everywhere. Word embeddings for language, sentence and document embeddings for search and retrieval, image embeddings that place similar pictures nearby, and user and product embeddings for recommendation. Embeddings are a quiet but pivotal idea, turning discrete symbols into rich numerical representations that capture meaning and similarity. Training a deep model is an experimental craft as much as a science. You need an architecture suited to the data, a loss function, an optimizer such as ADAM, training and validation data, and a set of hyperparameters to tune. Hyperparameters are the dials you set before training rather than learn from data, and they shape the outcome heavily. The key ones are the learning rate, the single most important to get right, the batch size, the number of epochs, the number of layers and neurons or filters per layer, and the regularization strength. There is no formula that hands you the best settings. Good values come from experimentation and experience. A modern deep network can have millions or even billions of parameters, so overfitting is a constant risk. The most dependable remedy is more training data, alongside data augmentation and dropout, which randomly disables neurons during training. Other defenses include weight regularization to discourage large weights, early stopping when validation performance peaks, a smaller architecture when capacity exceeds the need, and steady validation monitoring to catch overfitting early. Training a large network from scratch can demand more data and computation than most projects can muster. Transfer learning helps because early layers learn general purpose features like edges or broad linguistic structure, useful far beyond the original task. Deep learning strengths are formidable. It learns complex patterns simpler models miss, discovers features automatically, excels on images, speech, text, and video, keeps improving as data grows, and supports transfer learning across tasks. It is the foundation of modern artificial intelligence, but the limitations are just as real. It often demands large amounts of data, can be slow and costly to train, is hard to interpret, and requires careful, experiment-heavy tuning. It also overfits readily on small data sets, and it can absorb and even amplify biases present in its training data. Here is the key point. Deep learning is powerful but not universal. Unstructured tabular data, gradient boosted trees, and random forests often match or beat it while training faster and explaining themselves. Save deep learning for unstructured data. Let us build our first real deep learning model. This code loads the fashion MNIST clothing images, scales the pixel values into the 0 to 1 range, and builds a simple dense network with two hidden layers, dropout for regularization, and a softmax output over 10 classes. The flattened layer unrolls each 28 by 28 image into a vector of 784 numbers so the dense layers can process it. A dense network, though, throws away the spatial layout of the image, treating nearby and distant pixels alike. This version keeps the spatial structure. It reshapes the images to add a channel dimension, then builds a convolutional network with two convolution and pooling stages before the dense layers and softmax output. The only structural change from the dense model is the front end, two convolutional layers, each followed by max pooling, before the data is flattened and handed to the dense layers. Consider a case study. An electronics manufacturer photographs every circuit board on a high-speed line, and engineers want software that flags defective units, so suspect boards are pulled aside rather than shipped. The traditional approach leaned on hand-designed features measuring edges, colors, and textures. A sensible, deep learning workflow instead collects and labels many board images as normal or defective, then splits them into training, validation, and test sets. Next, you pre-process and resize the images using data augmentation to expand the rarer defect examples. Train a CNN, perhaps fine-tuning a pre-trained model, and evaluate on the test set with close attention to recall, since a missed defect is costly. Finally, review the misclassified cases to understand the model's blind spots and deploy with human oversight, routing low-confidence boards to a human inspector. The following code trains the CNN from the case study on Fashion MNIST, which stands in as a proxy for factory inspection images. This implementation mirrors the case study. It builds a convolutional network on the Fashion MNIST images. In a real factory, the output layer would have 2 units for pass or fail instead of 10 classes. This CNN typically reaches over 91% test accuracy on Fashion MNIST, beating the dense baseline and confirming that learning local visual features through convolution is the decisive advantage for images. To summarize, deep learning is machine learning with deep neural networks, and its defining gift is representation learning. We toured the architectures that made it work and faced the practical realities of data hunger, overfitting, and interpretability. For further study, look to introductory deep learning textbooks, the TensorFlow and Keras documentation, the PyTorch documentation, applied tutorials on image classification and augmentation, and accessible introductions to attention and the transformer. The foundational papers are also worth reading. The Linnet work on document recognition, the AlexNet paper that launched modern computer vision, the ResNet paper on residual connections, and a practical textbook rich in Keras and TensorFlow code. That brings us to the end of Chapter 15 on deep learning, the engine behind so much of modern artificial intelligence.